Okay, that's what.
Thanks. Awesome. Thank you. Thanks for the invitation to present in this year workshop. The project that I discussed today is on use of fiber optics for structural health monitoring of bridges, especially for reinforced concrete bridges. First of all, need to acknowledge my Professor Brian Yui, our head of the school, who is involved into this project, and other colleagues from School of Science, Professor Simon Fleming from University of Sydney, and also Professor Gang Prusti from UNSW. So, so I start with the research background, and then I talk about why we selected this kind of approach. And I briefly discuss about the case study and the approach that we took in terms of development of advanced fiber optics and digital twin model of the project. So the project, similar to Professor Huang, is quite earlier stages. We got funded, and we are hiring a postdoc for that. So if you have any good student, we will be more than happy to work with them. And the deadline for application is in 2 days. Obviously, we know that our structures are aging, and we see every day the intensity and frequency of natural hazards are increasing. So that's previously some people ignored that, but now it is really obvious for everyone. So one of the important aspects that we can address these challenges using sustainable materials and develop sustainable manufacturing techniques and construction techniques. So 40% of global emission is related to built environment. So it plays a very important role in terms of global warming. So one of the aspects that we talk a lot about it is obviously recycling, but recycling is one of the last priorities in terms of sustainability. So if we can improve the service life of the structure, it has much more impact in terms of reducing CO2 emission and improving sustainability. So that's why this structural health monitoring would be very beneficial for improving our built environment in terms of having more greener and sustainable built environment. The challenge for infrastructure in Australia, especially the transport infrastructure, is that they are mostly located in harsh environment, in marine environment. Most of our big cities are located in such environment, and that causes a lot of problem in terms of corrosion. So the estimation is roughly around $8 billion per year is spent on corrosion remediation and repair and rehabilitation. So this makes it very challenging for our asset owners to keep up with this corrosion process and have more sustainable and long-lasting infrastructure. So that is causing a lot of issues for specifically reinforced concrete bridges, because that corrosion usually occurs in marine environment very easily because of carbonation or acidification of the mortar and diffusion of that chloride ion into the system, and basically damaging the oxide, damaging the passive layer on the rebar, and oxidize the rebar, and initiation of the corrosion. So that makes it very challenging, and there are techniques to prevent that, obviously, but we have a large number of bridges that they have been constructed during the last couple of decades and probably in early 19, and that they don't have preventative measures for these kind of corrosion progress. So those kind of corrosion obviously are expensive and can be very catastrophic. Based on that, for example, in Transport for New South Wales and obviously in other road authorities, they have different types of methods, as I said, preventative methods and so on. But one of the interesting work that they do is using catalytic protection for already damaged structures. So that is almost the most successful method in taking chloride ions away from the reinforcement and increase the alkalinity of the concrete around the reinforcement, so protect the reinforcement from the further corrosion. So, but the problem with these kind of systems is that they are really costly, and the costs of these kind of systems varies between 1 to 10 million, depending on the size of obviously grid, and also the type of concrete or the environment they are located. If we have a large amount of chloride diffusion, and the type of reinforcement and so on. So obviously, if we can improve this performance using structural health monitoring techniques to give us some understanding before initiation of corrosion, that we can mitigate that initiation and mitigate the corrosion that prevents it from progression, then it can improve, that we can save a lot of money, obviously, and also we can increase the service life of the structure and obviously the sustainability of the structure. So structural health monitoring can help us to improve that and get a better understanding from the internal response and internal condition of the reinforced concrete structure. So there are methods like non-destructive methods for inspection, and different types of, for example, thermography or different types of image processing techniques, but they usually gives you understanding about the external condition of the structure. So what can we do about the internal condition? So we are lucky that at the University of Sydney, we have a good facility in terms of the fabrication of optical fibers, specifically for fiber bracket grating systems. We have this facility as our core facility, so our academics in the university can have access to that. And also Sydney Manufacturing Hub and ACMM for material characterization. So we teamed up with Transport for New South Wales and also UNSW and our science department to develop optimized, cost-effective fiber optics for these type of scenarios, specifically for corrosion, estimation and humidity, measurement of humidity inside the inside the concrete. So the objective is to develop these type of fibers and also interpret the data properly, and also develop a digital twin of the data. So that helps obviously Transport for New South Wales to improve the inspection method and analysis and condition assessment of their assets in New South Wales. The type of fiber optics we are going to develop is mainly focusing on measuring humidity and temperature, because we are looking at mainly on durability. Obviously, there are methods and fiber optics that they measure strain and temperature, but our focus is mostly on developing fiber optics that can measure the humidity within the concrete. There have been fibers that been developed all around, but the focus is for us is to look at develop these kind of, for example, polymer materials that we can cover these optical fibers in it, and for the specific type of condition that we have, because we have a lot of chloride diffusion into concrete and exposure to HCl, hydrochloric acid, and sometimes also sulfuric acid. So it's very, very challenging to use conventional method, conventional sensors, because they easily disintegrate and dysfunction after a very short period of time after installation. So the basic function of these fiber optics is they just work with light intensity, changes in light intensity, and as I said, we are developing that for measurement of the durability. On the other hand, we are also looking at how we can interpret that data and convert it to the useful information that we can get, because you have a lot of external factors like humidity, temperature variation, and also external forces like water splash and also the traffic on the structure. So we need to make sure we can calibrate these fibers based on that data, and finally develop a digital twin of the model. So I think I discussed about that last year, that was the project that we did with Lion O'Rourke, and we developed the digital twin model of the a pedestrian bridge. So that would be expanded for this project as well. Briefly, we can also connect that and couple that with finite element analysis and get the heat map of stress, strain, and also obviously humidity and chloride infusion within the structure itself. So as the final remark, we are trying to improve the performance, get a better understanding about the internal performance of the structure, and also get some alarm from in terms of the if the situation is the condition is very critical, so we can get very informed information from the structure and make informed decision based on that. So on that, I need to thank you and also all the collaborators, Transport for New South Wales, NSSN, UNSW, and Sydney Nano for collaborating with us. Thanks.
Thank you. So we have some time for discussions. Any questions? Yeah, I'll ask you first. Yeah.
The fiber optic sensors, is there any limitation on what length it can be used for?
In terms of the distance?
Yep.
We safely use them on bridges up to 30 meters, and they were not any issue. You definitely need to compensate that, but I think you have to consider it in your design and calibration.
And do we have like strain sensors separate from the temperature sensors, or?
We in terms of the fiber optics,
Yeah.
or yeah, we have a strain sensors, temperature sensors. There are some humidity sensors as well, but it highly depends on the type of environment you have, for example. And for example, it has been used in a very harsh environment like water treatment facilities. So those areas, very harsh environments, sulfuric acid, a large amount of sulfuric acid. So conventional system really difficult to give you understand internal performance of the structure. But with these systems, we can say they are safe and 100% okay, but they provide better performance and longer service life.
There's two more questions, sorry. The interrogator, is there any limitation on the number of channels that it can have?
I guess it's mainly depending on your interrogator and the cost of interrogator and so on. But I can't remember the one that we installed, how many channels we had. But I think it is mainly related to interrogator, the limitation about the channels.
And the last one, the sensors have to be glued or glued to the structure?
For example, with these systems, ICCP systems, you obviously create a groove and you put anodes in it and you cover that. But the challenge with that is the interference of that electrical, that potential and current into the system with the fiber optic itself. But similarly, you can create a groove and install it on the bridge here. Because this is very harsh environment, and the splash and high tide, low tide is causing a lot of problem for not only the anodes, but also for these kind of fiber optics as well.
Thank you so much, Ali, for your presentation. Very interesting. I have two questions. One is about the cost effectiveness of this technology comparing to the conventional SHM approaches. And the other one is about the digital platform. How did you develop the main digital platform? And then you assign the data later on.
Yeah, so in terms of the cost, that's a bit more costly. But for for example, for our application, we can produce fiber optics at university. So that is much more cost effective for us. The main cost would be the interrogator. But in terms of comparing to other methods that you can't use them for these type of applications, then I think the cost wouldn't be the issue because you don't have any other option to use to get internal performance of their structure. The second question was on the platform on for digital twin. I think we use very normal Grasshopper and Rhino system and Unity to create a digital twin model of it. And we developed a Python version of for connecting the data that we strain and temperature data, because that project was on a post-tension bridge, and we wanted to investigate the ALE shrinkage of that concrete performance. So we needed to have the temperature sensors in the system to compensate the calibrate the data and compensate the data based on the temperature. But yeah, these are the systems that I think that would be one of the areas that we can work on.
Thank you. Thanks.
Okay, next one. Yeah.
The question, I understand that the major point was to measure corrosion in the concrete, right? So you were measuring corrosion using fiber gratings.
Yes.
Can you elaborate how the sensor works?
So we are not measuring corrosion itself. We are measuring humidity. So that humidity, because gives you the understanding of how much of the solution penetrated into concrete, then we are not basically
So how are you
measuring.
measuring humidity in this case?
There are type of humidity fibers that optical fibers that you can use to measure the humidity, the same as temperature sensors and strain sensors. So we have humidity sensors for measuring the humidity amount of relative humidity in that concrete. Did I answer that?
I just wanted to see how the sensor works. So just
I guess the best person to talk about the sensor is my colleague in science and optical fibers, not me.
it's okay. Thank you.
So we have an online question actually. Whether Jianzhuli will raise this question.
I just repeat the question from online for you,
Sure.
Ali. And the online questions, hi, Ali, thank you for your presentation. How would you associate the extent of the deterioration in the rebar due to corrosion with a factor like mass loss, strain loss to the damage factor identified from the fiber optical sensors?
So I guess I guess I need to correct this understanding that we are measuring corrosion. We are not measuring corrosion. We are measuring humidity. And that humidity gives us understanding of how much seawater and colloid ions have been penetrated into the structure, because that penetration gives us understanding of if the corrosion is about to happen or that is already happened, or and based on that we can make a decision to inspect the bridge and do the remediation of the on bridge. So it's not measuring the corrosion itself. No.
Okay, thank you, Ali, and thank you.